So in the previous lecture, we looked at some ways you could use mathematical induction to prove really algebraic equalities, right? Algebraic equations or formulas. In this lecture, we're going to do something similar. We're going to stick with looking at algebraic sorts of things. But we're going to talk about inequalities instead. Okay, so we've got our first one here. For all positive integers n, this inequality is true. N is less than 2 to the n. Okay, now a positive is a word that can get us into trouble sometimes. Does 0 count as positive or not? Well, in this case, it's not something we really need to worry about because the inequality is true for 0. Okay, so let's start there, right? That's going to be our basis step. We're going to say if n equals 0, then 0 is less than 2 to the 0, right? Because 2 to the 0 is equal to 1. There's our base case. All right, so what do we need to do? We need to show, now for the inductive case, we need to show if n is less than 2 to the n, then n plus 1 is less than 2 to the n plus 1. Okay, how can we do that? Well, let's see. Let's start with this n is less than 2 to the n part. N is less than 2 to the n. And now, I know that what I really want to be talking about here is n plus 1, right? So let's do that. Let's add that. Right? Let's add 1 to both sides. This means n plus 1 is less than 2n, excuse me, 2 to the n power plus 1. Okay. Now what? Well, look, I know that 1 is less than 2 to the n, right? We know that 1 is less than 2 to the n because remember, n is at least 1 here. We've already shown this for n is equal to 0. So the case we're working on now are situations where n is greater than 0. And if n is 1, 2 to the n is 2, and that's greater than 1. And 2 to the n just gets bigger from there. Okay, so we know that 1 is less than 2 to the n. So here's what I'm going to do, right? N plus 1 is less than 2 to the n plus 1, which is less than 2 to the n plus 2 to the n. I replaced this 1 with something that was bigger, right? And if you replace it with something that's bigger, then the sum is bigger still, right? So, and now I'm where I need to be. This is n plus 1 is less than over here. That is 2 times 2 to the n. Right now we're going to use exponent rules. If I can this is right 2 to the first, and we add the exponents together, n plus 1 is less than 2 to the n plus 1, which is what we needed to show, right? And that's the end. Proof is over. Okay, so again, right, let's take a step back like we've done before, and think about the process here. This step here was part 1. That's the basis step. Then everything from here down, that was the inductive step, right? And my predicate here was this part. It was this inequality. So here I have, clear that up. Sorry, here I have P of n, and here we had P of n plus 1, right? So we did follow, right, the usual sequence of steps that we do when we're doing a proof by induction. So I've got another inequality for us here, and this one is a little different than the ones we've seen so far. And the difference is here. Everything we've seen so far, they all started at 0, right? Or possibly at 1. Now, we really do have a different starting point, and that's going to affect our basis step. The value that I'm going to use in the basis step for A is going to be 4. It's that minimum value for which the theorem, the inequality in this case, is true. And you can check that. That is an important distinction, because this statement is in fact not true for integers less than 4. For example, if you put 3 in there, 2 to the third is 8, but 3 factorial is 6. So this really doesn't become true until we get to 4. So let's go through our steps, right? The basis step, right? If n is, assuming not greater than, if n is equal to 4, then 2 to the fourth equals 16, which is less than 4 factorial, right? 4 factorial is 24. Okay, so there's our basis step. All right, so now what do we need to do for the inductive step? We need to show if n is greater than or equal to 4 and 2 to the n is less than n factorial, then 2 to the n plus 1 is less than n plus 1 factorial. All right, so how are we going to do this? Well, let's see. Let's start with that 2 to the n plus 1 part. All right, 2 to the n plus 1 equals 2 times 2 to the n. Just exponent rules. Okay, now, from the inductive hypothesis here, I know that 2 to the n is less than n factorial. Okay, so if I replace 2 to the n with n factorial, then this expression, it becomes bigger. So 2 to the n plus 1 is less than 2 times n factorial. Okay, now, what else do we know? We know that 2 is less than n plus 1. We know that 2 is less than n plus 1, because remember, n is at least 4. So n plus 1 must be at least 5. Okay, good. So I'm going to do this again. Right, now I'm going to replace 2 with n plus 1. So this becomes 2 to the n plus 1 is less than n plus 1 times n factorial. But n factorial is 1 times 2 times 3 up to n, and if we tack n plus 1 onto the end of that, it becomes n plus 1 factorial. And that's what we needed to show, right? And you can see it from what I've written there, but let's make it explicit. Therefore, 2 to the n plus 1 is less than n plus 1 factorial. And that is where we needed to end up. Okay, so now we've seen 2 different types of things that we can prove using induction. We've seen how we can prove equations or formulas, and we've seen how we can prove inequalities. In the next lecture, we're going to go in a different direction. We're going to kind of go back to number theory a little bit and show how we can use this induction technique to prove a theorem about divisibility.